Yeah, we will continue. And before that, we're moving to a different subject, not unrelated, of course, but different in the way we have approached this. So I have to make this recap. So this is from the beginning of this course up to now, this line. So we study linear system. We learn about modes. We learn about the solution of linear system. And then here in nonlinear system, we try to use our knowledge of linear system to predict how the system would behave. In the nonlinear system, we found multiple equilibrium points. And by getting the linearization of the system around equilibrium points and using the eigenvalues, we were able to anticipate how the system would behave. Then we moved to numerical integration techniques. With numerical integration techniques, we were able to obtain a solution numerically for all the variables in our system. And we used our own code using forward Eulers, for example, or trapezoidal rule, or the set of solvers that we have in MATLAB. Then we move to the power grid subject, and we discuss the behavior of synchronous generator. And we discuss the structure of this, and we have a question from Ryan last time. And we had issues last week with the recording twice. So I'm very sorry for that, but for the class on Wednesday, I put a description of what we discussed that day on Wednesday. But on Monday, I think we just went through general questions. And one of them was, what are actually dampers in the machine? So we talk about that that day and other things as well. So we review that, and then we went to model this synchronous generator. The first model is the classical model. It's not a model we use today for power grid operation or analysis. It's very inaccurate, but why did we study this? It was a starting point. It, from a conceptual point of view, it still makes sense because the model is simple and we visualize what is the meaning of voltage controlling the machine. And that came from an internal voltage. And by controlling the current in the rotor circuit, we can control the magnitude of that voltage. We learn about the angle delta. What is the meaning of the angle delta? We learn about the constant h of inertia. What is the meaning of that? We gave a physical meaning for that. So we use this classical model for that purpose. I believe in all times, maybe operators use it when computers were not everywhere. And they did the best that they could, and they have a procedure for that. And I need to give a clarification because I didn't specify the model. So for the model we study, we consider a voltage at the terminal, we consider a synchronous reactant, and we consider an internal voltage. But in practice, the classical model call these reactants the transient reactants. What is the transient reactance? If we use the two-axis model that we widely use, these can be approximated to XD prime. Yeah. These we can get a model for that, and we can have a physical meaning for this. This one is just, this model of the classical model is just a mathematical representation. It can be attractive because it's simple, but it has no practical meaning because it's very inaccurate. It will never capture the real behavior of a synchronous generator. But to be proper with the classical model definition, this is called use, not as synchronous reactant, but use as the transient reactant, which should be about XD prime. If you see the data we use, what I use for XS is the XD prime, more or less, yeah? So I think we use 0.2, something like that per unit. For this voltage, we assume that this voltage is fixed, given operating point and equilibrium point, we define how much was that voltage. In the classical model, this voltage is also called the transient internal voltage. And that is calculated with a given procedure. The procedure is right at the short circuit, when you have high current, then you calculate that internal voltage and you assume the magnitude of that voltage remains fixed. I didn't want to go into those details because we don't use this day the classical model for any practical analysis of any system. But to be proper, that is actually the classical model. It will require an internal voltage, transient internal voltage, that is calculated at the moment of the short circuit, and the magnitude remains fixed. And this one is called the transient reactance. That is about XD prime. Okay. Then we talk about the two-axis model. We introduced the part transformation, and we discuss what is the meaning of these DQ components. And the meaning of those are those variables related with the stators, because we are relating a stator that all the components remain stationary, but the rotor is moving. So what we did, all these current in the stator that are changing sinusoidally, when they are equivalently expressed at the rotor, they're stationary with the rotor. So that's why we got a D and Q component for the current from the stator. Now, IA, IV, and IC are expressed in terms of ID and IQ. The same thing for voltage, and the same thing for flux at the three phases. So we introduced that definition of DQ component, and we propose a two-axis model that we have used already in our example. The last part we did, just coding. We used MATLAB. We created our own script. We used the numerical integration techniques from the solver from MATLAB to solve this set of differential algebraic equations. And we use basically two solvers, which is OD15S, or we can use OD23T. Those are able to deal with differential algebraic equations. And that's what we did. We consider multiple examples. We consider, first of all, we consider here one machine infinite bus classical model. Then we consider one machine infinite bus two-axis model. And then we consider two machine, one infinite bus, two-axis model. And we got the definition. What was the difference between one machine oscillated with an infinite bus and two machines oscillated with an infinite bus? From a dynamic point of view, we discussed that maybe that last 1 or 2 weeks.
Two machines with a lot of energy going back and forth between the infinite bus and the two machines.
Potentially.
If they're oscillating phase.
Right. So in the other case was just one machine oscillated with the infinite bus. With two machines, potentially, if these two machines oscillate together, they will involve more energy in that oscillation. And what is the impact of more energy oscillating with the infinite bus? It's like a train. Can you stop the train right away? No. Probably will slow down. What about the frequency? What happened with the frequency of the oscillation? Probably the frequency would go down, right? Yeah, so the period of the oscillation would increase in that case, but potentially, because not always that mode will be excited. In the two machine infinite bus case, we have another option. What was the other option of potential oscillation? Against each other, you have two finite machines and they can oscillate among them. What is the energy involved in that oscillation? One machine was 3 seconds, the other 6 seconds. The energy is much smaller. What happened with the frequency oscillation? Probably it was a little bit larger. If that mode is excited, that's the manifestation that you will have in the variables. That's how the variables will oscillate. But if the other mode is excited, then you will have a more energetic oscillation and the frequency of the oscillation will be smaller. So that's what we observe in this case. Now we're moving forward. Now we're going to briefly discuss modal analysis. And for this part, at the beginning, we will use our own calculation. But at the end, when we deal with two machines, I'm going to ask you to use a code I developed with my PhD student. We will not go into the detail how we came up with the code, but you should be able to use it. Why? Because it's going to be a similar structure of what we had been working in class this semester. Okay? So you can use that. Any question? Any question? Now, if you move on this side, there is a homework. I will post the homework today. It will be due on Monday next week. And the midterm exam, the second, is going to be on Friday. Yeah? Are these good dates for you?
The homework maybe do like Wednesday, like at least 7 days to do it. Tuesday or Wednesday, maybe.
We can do that. It has been very hard this semester for me to grade the homework, but I might not be able to have your grade, but I will try to have the solution of the homework, so at least you can see the solution before the midterm exam. Would that be fine? Yeah. No MATLAB. No MATLAB. You might need a calculator, maybe. You might need to do a small calculation, but not big one. And question. Yeah. Conceptual stuff. Maybe I will put more emphasis in that. I'm not sure. Prepare to understand the concept, and maybe in the problems that the system that we analyze, maybe I will ask you something particular about the system. So you need to know. You need to know how to model the system or analyze the system, but I'm not going to ask you for everything, just a part. Yeah. Yeah, I don't remember all the equation by heart, so you can have your equation sheet. For example, the two-axis model, you can write it down so you know what is the model. You need to know how to use it. So that's what I'm going to evaluate everybody. Yeah? Okay. Any other question? Yeah. Here we go. Yeah. Modal analysis. So there is a lot of details about model analysis, but here I'm going to describe the most important aspect of modal analysis. And this has to do with the mode, and we discussed what a mode is in chapter 2 when we study linear analysis. So we start that from the point that we have a set of differential algebraic equations, and we discussed already how we came up with this representation. And we know that all these variables and equations related with the algebraic component, these are very a physical phenomenon that happen very fast, and we can approximate it as they can move infinitely fast. Therefore, they can change instantaneously at any time. That's how we have a representation for the grid. If there is a short circuit, voltage can immediately change and take another value at the short circuit moment, or when we clear the fault. The same thing will happen with the currents in the synchronous machine. You have a short circuit, this current instantaneously can take some value when a disturbance occurs. So that's how we came up with this model. So the model using the two-axis model for the machine, we're going to capture just the dynamic of the 1Q damper. The other 3 dampers that we have the 2Q, 1D, and 2D. Those are going to be assumed that they can respond instantaneously. Yeah. So that's the assumption for the two-axis model. At the end, we will have this mathematical representation. Now, uh, if we're going to study the behavior of this, then we have one complication already. Because what we studied before in chapter 3, we studied nonlinear system. And we apply our knowledge of linear system. What did we do? First of all, we found the equilibrium point. And around the equilibrium point, we linearize the system. And then we propose, well, what about if the system moved very close to the equilibrium point, and then the linear model is an approximated representation of the system? If that is the case, then we calculated the eigenvalue of the system of the linear model, right? So we did that. But when we apply that, we didn't consider any algebraic equation whatsoever. So now our model is like this one. The question is how we can get eigenvalues now when you have differential and algebraic equations together. We still need to get the equilibrium point, yes, but then when we get the equilibrium point and we linearize this equation on the equilibrium point, how we're going to get the eigenvalues? That's the question. With this set of differential equation, we can represent any system. And here is an example of what we did in chapter 6. This is the finite machine connected to an infinite path through that line. And in this case, we use the two-axis model. So in this system, then we have 4 differential equations, which are here, and 2 algebraic equations. As Ryan mentioned at some point in our discussion, we didn't need the explicit determination of the voltage at the terminal. Why? Because the system was so simple and we could express the internal voltage of the machine directly with respect to the infinite path that was fixed. So in this case, the algebraic representation is very simple, this one, yeah? But when we consider the two finite machine and infinite bus, that was not possible. We needed to determine the voltage at the terminal. Well, for this system, that's the differential algebraic representation. So for the state variables, we have this vector, and for the algebraic variable, we have this vector. And we need to find the equilibrium point for the system. And when we find the equilibrium point for the system, then we need to linearize the system around the equilibrium point. And if we proceed in the same fashion as we did before in chapter 3, we should be able to obtain something like this. So here, what do we have? This is a vector. How many components do we have? 4 components. Each component is going to be the derivative of our state variable. So here, we're going to deal with the function f. What is the function f? f1 is going to be this function. f2, this one, f3, and f4. It's a vector of functions. Those are the components of the vector function. And we need to take that function and get the gradient with respect to the state variables. So for this part, we will get the Jacobian of the function f with respect to the state variable, the derivative of each function with respect to each state variable. But also now, because we have algebraic variables, we will need to add this new component. And this will be the derivative of the function f with respect to the algebraic variable. So we need to determine this new matrix. But that's not the end of the story, because we have 2 algebraic equations and we need to proceed in the same fashion. In that case, because these are algebraic variables, this side of the equation will still be 0 and will relate directly the changes of the state variables with the changes of the algebraic variables. Algebraic variables can change instantaneously. So if x has a change, that will mean that y instantaneously will assume a different value. So that's the algebraic representation. Here we will have a matrix, which is the derivative of the function vector of function g. First term of the function g will be this equation, and the second term of the vector function g will be this function. So those functions are going to be derived with respect to each of the 4 state variables. So we will have a matrix here. So again, what is the size of this matrix? It's going to be 2 rows, 4 columns. This one, 4 rows, 4 columns. This one, 4 rows, 2 columns. And finally, this one is the derivative of g with respect to the 2 algebraic variables. So this is going to be 2 by 2. Okay. Now, how do we get the eigenvalues for this? Before, what did we have before? Do you remember the representation before? Before we have just one vector, the state variable, and we obtain the system matrix and relate this with the same vector. This is the derivative of the vector of a state variable. This is the vector of a state variable, and we obtain this matrix. By calculating the eigenvalue of this matrix, then we were able to solve that system. So we need to take this system into that form. Yeah, so that's the newest step we need to apply here. But what we're going to do from this equation, what do we have in this equation? A unique relationship between delta x and delta y. It's unique because if these matrices are determined for any change in x, we will have a specific change in y. This is specific. So we can use that equation and solve for delta y. How? By multiplying this equation by the inverse of this matrix. So if we multiply this equation by the inverse of this matrix, this is going to be multiplied by the gradient of g with respect to y inverse, multiplied by this, plus delta y. So we can isolate for delta y, and we get this expression. So this will be possible when this matrix has an inverse. We'll be always able to find the inverse of a matrix? Yes or no? No? Why not? Are not invertible. Why not?
I believe an invertible matrix is only matrices with a determinant.
Perfect.
Yeah.
So the matrix need to be invertible. Sometimes when you have the operation in the system, if the system is highly loaded, potentially this set of algebraic equation can be not invertible. That means that the determinant of that matrix will be 0. In that case, we cannot use this model. This model will fail. But trust me on this part, most of the time, this singularity, when we cannot get the inverse of that matrix, will happen when the system is very stressed. If that is the case, we might not be able to apply this model. Let's assume that the system is not really stressed, and this is going to be invertible. Yeah, most of the system we will study will have that property. So we will be able to, given a set of vector delta x, we will immediately know how much is delta y, because they can respond instantaneously. If we know delta y, then we can replace that in the first equation, and we replace that expression for delta y right here, as you can see here. There it is. We change the sign because of this negative sign right there. And then we can factorize by delta x from the right. And finally, we get the matrix of the system we were looking for. So what we need to get is all these 4 matrices. This procedure is called the Cron reduction. It's called Cron reduction. Yeah. So that's what we have to do. When you have that matrix, then we apply what we had been doing. We need to get the eigenvalues, and then we will have this diagonal matrix with the eigenvalues, all of them determined. We will have a matrix of transformation Q with the columns being the right eigenvectors of each of these eigenvalues. And we're going to use these to transform the system, and we can solve for the transform variables. We call the transform variables how? Do you remember? We call it y. And we're running out of letters here because we call already y the algebraic variables, not the transform variable. I need to fix that. We're going to call it now the transform variable w, okay? So w is going to be q inverse multiplied by delta x 0. And delta x 0, what is delta x 0? What do you think? We're linearizing this with respect to the equilibrium point. So what is delta x 0? We solve this, the initial point with respect to the equilibrium point. So if the variable is 1, whatever it is 1, whatever unit, 1 per unit, whatever it is, voltage, current. If the variable is 1, then delta x 1 means that the variable is 1.1 per unit, because all this model is referred to the equilibrium point. So we will have an initial condition here, and with that initial condition, then we can transform the set of variables into omega 0 by using the transformation. With that initial condition, we get the solution for omega, which is exponential of lambda t omega 0. Why? Why we can do that? And we discussed this a lot in chapter 2. Why can we do that? Why do we think that that's the solution? Or maybe a question in the final exam. Not for this midterm exam, because this is chapter 2, but
Because the matrix there on the left is
diagonal.
so it's all decoupled.
All decoupled. That's the key. Perfect, David. With that, then we replace the value of omega 0, and then we get a solution for omega. We have an explicit solution for all the omega. When we have that vector omega for all time t, what do? We apply the transformation backward. So we multiply q by omega from the right. And in that fashion, we get the solution. Yeah, is that clear? This is exactly what we did in chapter 2. The only difference now is that to calculate the eigenvalues and the eigenvectors and the matrix Q, we need to eliminate the algebraic variables and equation from our model by applying the reduction, Cron reduction, as I discussed in the previous page. But from here, we can get two important things. Look at the equation. What can we say about that expression in regards to delta x 0? Because that matrix exponential of lambda t is diagonal, right? It's diagonal. What can we say if you look at this part of the equation? Q inverse delta x 0. That's the initial condition. What would you say? Is there anything we can say about that? Well, Q inverse delta x 0, what is that? You're multiplying a matrix by a vector. What is the result of that? A vector. And that vector will be multiplied by the matrix exponential of lambda t. And David said that matrix is diagonal. So what is the meaning of each of the component of this Q inverse delta x 0? Because it's a vector. You have a vector. How many terms will that vector will have? Delta x 0, right? How many for the system we just saw before? The single machine infinite bus with two-axis model. 4, because we have 4 state variables. So the vector Q inverse delta x 0 is a vector of 4 terms. But because the matrix exponential of lambda t is diagonal, what is the meaning of each of these terms? Is a component. Let me put it here. So here we will have for, yes, exponential lambda 1t, exponential lambda 2t. Let's make it with 2. This is another system. So this is going to be exponential of lambda t, when with lambda being this matrix with the eigenvalues in the diagonal, right? Exactly that. And here we will have the other term, q inverse delta x0. What do we have here? I said another vector. How many components? How many components we have here? 2 in this case, then we have 2 terms. The question is, what are these terms? When you do this multiplication, what you are going to get? First mode, multiply by this, plus 0, right? So in the first row of this new vector, because this is a new vector, will be this component multiplied by the mode. Second equation, what do you have? This multiplied by 0 plus this multiplied by this. You will have a new component term that will multiply this. This is kind of what is the amplitude you're going to get somehow in that mode, right? Are you with me? So when you look at that equation, you can think about this term as that. What about if one of these terms is 0? What will happen in your solution? That mode will not appear, right? Are you following me? So this part is going to be related to the excitation of the mode. So this term can be large, can be small. If they are small, that mode has not been highly excited. If that component is large in magnitude, that mode has been highly excited. So this term will be related with the excitation. Okay? We talk about the two finite machine infinite paths, and we said, well, we have two different type of modes. One, when the two machines oscillate together with the infinite path. So in one of the simulations, we have that situation. Do you remember what we did? I don't remember, but we changed the inertia somehow. We kept the short circuit at bus 2, which changed the inertia, and somehow that disturbance excite that mode. Two machines oscillating with the machine. And we got this. It's exciting that mode importantly. But in the other case, another situation, other data, that short circuit excited the other mode. Which other mode? The two machine, finite machine oscillating against each other. That happened because of this. So some disturbance will excite one mode more than others. You change the disturbance, something else will happen. So the modes, not all modes are going to be excited in the same proportion. Yeah. So that part is related to the excitation of the modes. So disturbances will have, different disturbance will have a different impact on the dynamic behavior of the system. What about the other part? We have the other part. When you have that result for this exponential of lambda t in this term, then when you have that vector, then you need to multiply that by q. What do you think that will happen? We look back here. So the first term in your vector will be, for this example, whatever excitation you get here, whatever term you get here, is going to be the weight we're going to have on this mode. It will be how excited that mode will be. So the result of this, the first component of the vector that you get after this multiplication is going to be that term that will excite that mode, amplify that mode, 1. So when you have that component, then you need to multiply this vector by q. So what this component will always be multiplying in that matrix is the first term of the vector. Which column is going to be always being multiplied by that term? The first column, first column. So it's the same mode that has been excited through the initial condition. But how the mode will appear in the different variables in the system will depend on what we have on that first column of Q. Yeah? So what about if that column of Q has a term that is 0? That mode will not show up. Will it not show up because we didn't excite it? No. Will not show up because Q in that term is 0. Why not? Then we have a different concept there, is physically, that mode will never be observed through that variable. That variable will have nothing to do with that mode physically, and it will not show up. Another thing, maybe it show up, but what about if we're looking at the example where we have the two machines oscillating together, the two machines oscillating together with the system? What happened in that case? Two variables, which one? Omega 1 and omega 2, moving, increasing together and decreasing together, right? They're together. How do you think the term related to the speed omega 1 and omega 2 will be related to that mode? Will be similar. These are all complex quantity, right? Q will be a column. The first column of Q will be complex. What about if one is +1 for omega 1, but for omega 2 is -1? What is the outcome of that? The same mode, but in one is as it is, but in the other variable is the opposite. What is the meaning of that? The meaning of that is that while the mode will be there in one variable, and the speed is increasing, for example, in the other variable, the same mode will be there, but the speed will be decreasing. It's in opposition. So if we compare that component in the column related to the mode we're studying, we can see how is going to be the manifestation of that mode in all the variables. Because these are complex, we're going to look not at the magnitude, but we're going to look at the angle of that term. In the case when that component for one variable is 1 and the other is -1, what is the angle of this? 0. What is the angle of this? 180 degrees. So in that case, we will say that they are in counter phase. Why? Because generator 1 is oscillating against generator 2. When generator 1 is increasing the speed, generator 2 is decreasing and backwards. Right? So we will look at the angle. In the case the two machines are oscillating together with the infinite path, both machines will increase the speed together or decrease the speed together. So in that case, we will have something else. And this doesn't need to be real numbers. It may be 0.5 plus j 0.5. What is the degrees here? 45. Here might be 0.8 plus 0.8. How much you have here? 45. So the angle is the same. So the manifestation of the mode in those variables will be at the same time, the same type of behavior. So we will say the behavior will be in phase. So the two machines are together. Right? You understand the idea? We are going to call that behavior, we're going to call that the mode shape, as we have in the figure right here, mode shape. Yeah? Final definition, and we're done with this set of definition, and we will look at the example and apply all of this. We need to define an important thing, because most of the grid codes we have in the power system out there pay attention to the damping ratio. The damping ratio. What is the damping ratio? It's simply a measure of how fast an oscillation will damp. How fast. In practice, we would like all the modes in the system to have at least a damping ratio of 10% at least. Yeah? So if you have 30, you're fine. Very fast dampening of the mode. If you have a contingency, what can be a contingency? If you have a contingency, maybe a generator outage, maybe a line outage. If something changed in the system, the mode might change in the system. Well, if you have a single contingency, that at least the mode should have 5%. Maybe not all grid code will consider this, but most of them will. Yeah. The definitions. If you have an eigenvalue and you have the mode that has an eigenvalue lambda I, that mode will have a real part and an imaginary part. This is in rectangular coordinates. In polar coordinates, it's going to be the magnitude of that complex quantity multiplied by exponential of j theta 1, which is the angle of that component. So either in rectangular or polar form, that's the definition of the eigenvalue. So the magnitude of this, and here we have the eigenvalue in red. So the magnitude of this is going to call the natural frequency. The natural frequency. So as you can see here, you can draw a circle with that radius. So that's the circle that you have for the natural frequency. When the real part is 0, then the imaginary part will be exactly the natural frequency. Then we have another definition, which is what the main aspect of this set of definition, the damping ratio. Damping ratio is sigma I, because we're dealing with the eigenvalue lambda I. It's going to be the negative of the real part divided by the magnitude. And when you do that, you get an a-dimensional quantity. You can calculate this and use the magnitude, the natural frequency for that here in the denominator and get a number. Or another thing you can do, you can use the negative of the cosine of the angle of that eigenvalue. Either way, you will be able to determine the damping ratio. If you this is a quantity a-dimensional. So if this lambda I is 0.1, what is the percentage of that? It's like per unit. How much is that? 10%. Yeah. So those are the numbers we will get here. And there are other definitions as well. Another one is the frequency of the oscillations. So the frequency of the oscillation will be the imaginary part that you have for that eigenvalue, this term right here, below the natural frequency, this component divided by 2 pi. And that will give you the frequency in hertz. If you get the inverse of this, you will get the period of the oscillation. Right? Are you okay with this definition? Yeah, it's a pure definition. The most important one, all of them are relevant, but the most important one is going to be the damping ratio. Example, we have a few more minutes. This is the infinite bus, the single machine infinite bus system. And to start with, let's use the classical model. We know this is not a model we use for real system, but it's simple. And it's good as a starting point. Why is it going to be so good? Because we just have 2 state variables and no algebraic variable. It's very simple. So this is the set of equations, and we did it before in chapter 5. And this is the equilibrium point when the machine is injecting this power, 0.5 per unit. That's the equilibrium point. And this is the linearization of the system around the equilibrium point. So delta, angle delta, is going to be whatever angle we have minus the equilibrium point of that angle. Delta omega will be whatever speed we have minus 1, because that's from the equilibrium point. So when we have the equilibrium point and the matrix A evaluated at the equilibrium point, we have the matrix, we calculate the eigenvalues and eigenvectors, and this is what we have right here. We can calculate the frequency of the oscillation. We take the imaginary part of this divided by 2 pi, and then we have 1.4 hertz, roughly speaking. And if you get the inverse of that frequency, then you get the period, which is about 0.72 seconds. In the last part of our study, we ran time domain simulation. And this is what we got, I think, when we clear the fault at bus 1 at time 0.3. Through time domain simulation, what we got? This behavior. But if you look very closely here, what is the period of this? It's very close to what the model analysis was telling us in advance. So because how many modes do you have in this system? It's a system with 2 state variables, 2 differential equations. How many modes do we have? 2. What kind of mode? exponential decay, or what kind of mode? Or is the eigenvalue real? No, it's not real. It's complex. How we call the equilibrium point in that case? Stable, focus. So it's actually one mode, because the second one is the conjugate of that, right? So it's just one mode. And what is the dynamic behavior of that? The machine oscillating with the machine. We just have one mode, basically. And what do you see in the time domain simulation? Just one mode of oscillation. And that is very close to what we determined here. And again, we can, yes? No. Oh, yeah. If you have a pair of complex conjugate eigenvalues, that's related to just one physical mode of oscillation. Yeah? In this case, is that single machine oscillating with the infinite bus. But in the other situation, when you have two finite machine and an infinite bus, we calculated in that case 4 eigenvalues related to the motion of the machine, but those are pair of complex conjugates. So we have actually 2 physical dynamic behavior for that machine. The 2 machine oscillating together with the infinite bus, or the 2 finite machine oscillating against each other. Yeah. And that's what we got. So there is consistency there. What about the excitation? Well, at that time when we clear the fold, those are the variables that we obtain for delta and omega. We calculate delta angle and delta speed with respect to the equilibrium point. Those are the variables. We put them here and we got this number. What do we see? Well, in this case, it's trivial because you have one mode. The only mode in the system has been excited. And the numbers that you can see here, these are complex conjugate, right? The only mode in the system has been excited. What about the mode shape? It's one mode. So let's look at the first column of Q. This is the first column of Q. What is the angle of this? 0. What is the angle of this one? 93 degrees. What is the meaning of that? Does it make sense? We're comparing here not speed with speed in the machine. We're comparing angle and speed in the same machine. How is the derivative of the speed defined? If you have the derivative of the speed, that is equal roughly to what? Acceleration, and that is how related with the angle. Is the mechanical power minus the electrical power. The electrical power is P max sine of delta. What about if delta is very small? How much is sine of delta? Delta. Sine of delta is equal to delta when delta is small. So the derivative of the speed is related directly to delta, right? So how do you get the speed? Basically, the integration of delta. So omega will be leading delta 90 degrees, roughly speaking. What do we get in the mode shape? Exactly that. Okay. This, if you compare delta and omega, we cannot discriminate about what is the exchange of energy in the machines in the system, because you just have one exchange, which is the finite machine with the infinite bus. But here, for completeness, we can calculate at the angle and we can observe the relationship between delta and omega will be leading the angle 90 degrees. And by definition, by the model we have, yeah, that's correct. That's about what we got there. Yeah? Yes.
How do you know that it's excited versus not?
It's the only mode. So whatever number we have here is going to excite the mode. Any disturbance will excite the only mode we have. When we have two machines, then it's going to be evident because it's going to be relative, and we will see one with respect to the other. No, this is just a quantity. We don't know that it need to be just farther from the equilibrium point. It may be how has drift away from the equilibrium point. That's more important than the magnitude itself. But then you will have two modes, for example, and one mode will have some magnitude. And if you compare with the magnitude of the other mode, then you can say something. Oh, this mode is 3-4 times the excitation of the other mode. Then you expect that that mode will be manifested more importantly in the variable. Yeah. Finally, we have just a few more minutes. Damping ratio. So we have the eigenvalues. We have the real imaginary part of the eigenvalue that is right here. We use that. Apply that in our definition for the damping ratio. We just have one mode. That's the value we got. 5.7%. Is this a good system based on the grid code? Maybe not, right? But after a contingency, well, the system is so small, I don't know what kind of contingency we may have. We have a contingency and the generator is out of the system, so there is nothing after that. But we should expect 10% in that case. It's not that great. So if we plot this in the complex plane, we have this. This point here is the eigenvalue. The conjugate of this is right here. We don't need to look at the positive and negative in the imaginary axis because it's flipped. It's like a mirror. So what we're going to do from now on, just look at the second quadrant here. Yeah, because in the third quadrant, we will have exactly the same. So in this quadrant, or the third quadrant too in this case, but we can draw the lines in which we're going to have either 5% and 10%. You can see there is close to the one in 5%. So we can have this diagram for any system. We can look at the modes, see where they are, and see which might need some correction. What is the correction that we will apply? We will have to design a controller. We will put a controller somewhere in the system that can push this mode away from that region. Hopefully, this mode is anywhere on this side, right? That's what we want. So this mode can be anywhere on this side. And we're going to talk about this next class. What we're going to do here, same analysis, modal analysis, but here is the two-axis model for the synchronous generator. So we will have 4 state variable. In terms of the motion, kinetic energy in the machine, how many modes we will have for that, just that behavior? Just the motion, one machine that might get energy and release it back to the infinite bus. We will have just one mode related to that behavior. We have 4 state variables, yes, but only one mode will be related to that behavior. Which mode is going to be? We will see. It's going to be the slowest behavior possible because it's so much energetic, it will take more time to develop in time. And typically in the power system, those are going to be the dominant modes in the system because they are more energetic. It's all that kinetic energy stored in the rotating masses in the machine, the most critical for the power system. So we will take it from here. We will apply it to the two finite machine infinite bus, but we will use the software that I'm going to put in Canvas so we can use it as a tool. So we will not have time to derive everything because it can be very messy. But at least we will be able to discuss these two simple systems to later use a tool to study larger systems. Any question before we close? Yes, two questions.
Omega 90 degrees ahead again in the previous.
It's because of the definition. So look at the changes in the angle with respect to omega, and we look at the changes of omega with respect to the angle. One is the derivative of the other one. Yeah. So the derivative of the speed is going to be related to the negative of that angle, right? The derivative of the angle is going to be related directly to the positive of the speed. So that will create that shifting of 90 degrees. the speed will be leading the angle 90 degrees in a machine. Yeah. Okay, guys, I will see you on Friday. Oh, last question. I'm sorry. Last question.
For homework, is it going to be covering chapter 6?
It will cover what I deleted here, time domain simulation. So basically, you need to go to Canvas. I put a message with a lot of details of what we discussed. It's going to be along that line. You will have your system and you will have to analyze the behavior of the system and get conclusions. So that's what the homework is going to be. Thank you, guys.